So welcome to demonstration video 1 of B07, our course on using R packages, where we're just looking at here in this video, tidy data in R before we move on to more advanced things in the other parts. So we're going to look at a few things in tidy data, and we need to install two key packages to get this working. The first one is called dplyr. So if we just run that line on line 20, hit no if you ask the computer asks to restart, and that will install dplyr there for us. And we see that downloaded the file, it downloaded to the folder. So if we run line 21 to check that we can activate the library, we can see that it's all, used, has functions of the same name as other packages, but that's fine as long as we are able to select the right function. And one way of doing that, just for your interest, is to type in dplyr and then 2 colons after each other like that. And then you can select a variety of functions associated with dplyr, like select. Let's uninstall tidyr in the same way. Hit no, let it install. It does the same thing. It downloads a local file to store the commands there. We activate tidyr on line 23, and it all looks good. So that means we can move on to the interesting parts of what we're going to look at today, and that's this special symbol called the pipe symbol. So to pipe means to send data. So we're sending data out, and we're going to be dealing with big data sets. So what we're going to do is send them through several different commands, one after the other. Just like you might select people that are, say, taller in a class, and then you might want to select the people with brown eyes, and then you might want to select the people that live in Woking, for example. So that's kind of what we're doing here. We're taking data, piping it out to function 1, piping it out to function 2, and that can iterate on as many times as you want. What's good here is that you can build the functions up. You start with data to pipe to function 1, see if that works, and then you add on the part here for function 2, see if that works, and so on and so on. So to build these up iteratively, I'm going to look at the example of the select function in the whole tidyverse. So the select function is very handy. It's a bit like a subset. So you want to recall we had subset before, and we can subset iris, and we're going to look at, I don't know, sepal.width greater than maybe 3. And there's a bunch of them there that are greater than 3. Select is very similar. So we can go to iris and we can pipe it out to select. I'm going to say sepal.width, for example, and that selects that column only. And then if we do sepal.width greater than 3, you'll see that it doesn't actually do numerical calculations at all. So this is for column selection. So there's actually other commands then. We have to pipe it further to select sepal.width is greater than 3. Or we can actually put it in at the start, but that's not here. What we can do here is select specific columns that are of interest. So for example, we can select sepal.width and sepal.length. And you see those 2 columns are now selected only. Another one is filter. So filter allows numerical calculations. So instead of doing our previous command, sepal.width greater than 3, we can instead type it further out to filter and type in there sepal.width. And what's our criterion? Greater than 3. That's what we're looking for. We run that, and you can see all the columns now have a sepal.width greater than 3. If we want all the columns with that, we can just use filter on its own. So we don't need that select function. There we have all of them there. And if, for example, we want to pipe it out, so we get, select, we want to filter the species is equal to Setosa. We can do that as well. So you can see there we have Setosa only. But we can also, here in this example, use the quantile function as well. So we could have a more complex request using the quantile function, which looks at the basically the percentile threshold. So here we want to look at this percentile threshold of sepal.width, And then we put in at the end as a second argument to that function, the percentile that we want. So we might want the top, the tallest plants. So 0.9. And there, when we look at sepal.width, you can see that you have the taller plants. If we do 0.1, that should be, if we look at sepal.width again, there we get a wider range of plants. So you get the ones that are in the top 90%. So let's remember that quantile, if we look at this quantile example, is simply determining a threshold value for the 10th percentile for that particular metric. So to get that, we'd have to give the exact array that the data frame that we're looking at. So iris $sepal.length will extract that as a vector, and then we put it in the quantile function, and then we get the threshold. If we could do 0.9, you can see there it's 6.9. And then what we're doing with the lengths is that we're just sending a vector of lengths to the function. Okay, filter, group by. So group by is very convenient here. So if we look at the previous function we had, so we're selecting the ones that are, let's say that the top half, we can pipe it out and then say group by, because we want to look at the information per species. So group by species is quite convenient here because we have 3 species, Setosa virginica and versicolor. We press enter here and it will organize it by species. So you see here at the top, we have a tibble. So it's a type of flexible data frame that's common to the Tidyverse. And then we're looking at the quantile, and we're looking at sepal.width 0.5. And it could be a good example here if we look at a more stringent threshold, let's say 0.95. Yeah, what you see here is that because we have grouped by species at the end, and we have this query first, this is taken the top 5% of plants based on their sepal.widths across all sets. So what we can do with group by, if we want the top 5% per species, is simply put that first. So we delete this part, put group by at the start, and then pipe it. And then we have the top 5% in each species instead. So group by can be used at different stages depending on what you're actually requesting from it. We're asking for the 5% tallest plants across all species, organized by species, or you're looking at the top 5% of plants per species. So that's a kind of a flexible way of trying to grapple with our data. Arrange. So you might want to basically sort your data in a particular fashion. So if we look at this one, even we can pipe it out to arrange, and we might ask then, we're going to arrange it by sepal.width for ease of viewing. So if we do that, we can see the sepal.width is organized by that, and it happens to correspond to a species by coincidence. And we do it by descending as well. Default is ascending, so it gets higher as you go down. Else descending, so we see the highest sepal.width is first. Okay, gather. So this is now a big function. This is a key function. If you don't learn anything, at least learn how to gather your data, and that converts your data from being the wide format where we have a bunch of columns with different features. So it could be like different genes, and then we have our rows, and they contain different samples. And you've got this big table. Gathering it turns into a long format. So long format, we have a column with each sample at first, and then we have where there's multiple rows per sample. Then we have the second column with the first major feature of interest. And then we have the third column with the second major feature of interest. So it could be your blood before the experiment for a certain patient. And then at the end, we have the value itself. And that will mean each row has a single value. and has effectively metadata before that. So that means it's very, very long. So, and if you look at the introductory videos, we have an example of that where we have the WHO data, where it's 262,000 rows on COVID mortality data, and it's in a long format. So just one value per row, where they're looking at across different countries over time per day information. So we can do that with Iris. So what's worth noting is that we also want to take the column names here as well as arguing to the function. And so what's worth noting as well is these names for the keys and values. I just random names. They doesn't really matter what you want to call them. So let's just get the head of what we're going to produce here. So we're going to gather our data sets. We put in Iris first. And then we go, okay, I'm going to kill my key. I'm going to call it key one, just so you can see what it is. And then I'm going to call my value. Gonna call it value one so you can see it up here. And then we have our column names from Iris. I'm just going to paste it in. So our column names go last. So if we look at the head of this, what we see there is that we have gathered our data. Now it's organized by species. Then they have key one and value one. So we could, for example, change value into observation if you want. And the key one is the, I don't know, feature. And if we go through that all the way through, view it. Oh, lost the round bracket. Yeah, we go from Setosa sepal length, scroll down to sepal, versicolor sepal.length, Virginica sepal.length, and Setosa sepal.width, and so on and so on. And we've got 600 entries because we have 150 entries at the start with 4 features. Consequently, 4 features by 150 rows is 600 entries, which corresponds to the number of rows here. So it makes it long. So you can kind of predict the number of rows you have depending on the dimensions of your table and what way in which you want to gather it. So if you give it only part of the columns, it'll make it into a bit of a mess. So if you see here, let's just give it 2 column names, and this will be pretty hideous. When we look at the result, yeah, so you see petal.length, petal.width is like half of the old table. You got Setosa, then you got the feature, and then the observation. So it's now 300 entries, so that's pretty useless and confusing. So don't do that. Yeah, so we have these things. We can try this one on line 81 to see what it does if we just leave out the species. You see, it puts it in there anyway. And then if we leave out the columns completely, it should return the original table. Yeah, it doesn't. Yeah, it leaves out the species, which is not. It has them at the end, so that's a mess again. There we go. Okay, so later we'll gather our data. Another example is mutate. So mutate, so we can take our iris data and we might want to pipe it out to filter it like we had before, sepal dot width, length, whatever. It's greater than 5. Okay, that gives us information, and we might want to mutate to rescale the data. And because we have continuous numerical data there, that notion should conform to a normal distribution, perhaps, if we plot it. We could kind of look at the deviation of, we'll just randomly call it dev, of sepal.weight, and we're going to have to scale it appropriately. So we're going to look at the mean. So it's taking the mean of each observed value of sepal.length away from that value. So we could scale that perhaps. We could perhaps scale that by the standard deviation of sepal.length if we want. And that will create I forgot yeah, you can see that at the end. Now we have a metric indicating the extent to which sepal.length deviates from the mean scale by the standard deviation. So it kind of depends what metric is most of use to you. If we unscale it, yeah, we could, for example, look at the difference between completely different metric, sepal.length minus sepal.width as well. And you see there, you get positive values all the way through for the final column there, dev. So that's mutate, another convenient function for basically adding a new column. Summarize is also very convenient because we may want to summarize information about a whole feature of interest. So I know getting a mean is kind of a oblique way, let's say a standard deviation is an oblique way of getting that result, but it kind of illustrates what you can do with summarize. And what we might do is add in group by species and pipe it to summarize. And then we got the standard deviations for each species. So that's where it becomes more convenient if you have multifactorial data with many groups. You can get the standard deviation for each of them. So that's summarized as well. It gives you numerical information depending on what you want. So this is an example in the illustration of getting the quantiles to in the same way that we did before. Separate is handy for strings. So if you have numerical string data, like the species names here, you can separate it using this function separate, but it's separating it by character. So you need to give it the character by which you're splitting it. You need to give a sep at the end. Sep equals I is a good example here because there's I's in certain species. Or we could try E. And how many columns do we need? We need, let's call it 1, 2, 3, 3. That's probably enough. Let's see what we get. Must be a character vector. A, B, C. So you can see there for Virginica, it was not split because there's no E. For versicolor, we have V and orsicolor. And then Setosa, we have S and Tosa. So E has been taken out and it's been split into these two columns. So we can tidy this up a bit by just removing that and then maybe viewing it. So you can see that more easily now. We just split Setosa. So if you have, say, some sort of metadata in your sample name, that could be actually handy for extracting that information and splitting it into columns. So now we have an example using filter and gather together, and this uses a more complex data set that's more real. The Irish boys' names, it's got 46 years and over 2,000 names inside there. So it's a large data set, which, you know, is fairly heterogeneous because there's missing years. There's a lot of missing zero data, NA data. It's kind of reflexive biological example. And what we can do there is, you know, if you want to take names, we're taking names. Oh, we could filter to get what are you looking at? The years 2000 and something. Oh, it popped up. 2004 with a high frequency in that year. Oh, we see none. Okay. Oh, that's surprising. Aha, the query is not correct. So let's look at names. And then we have, let's look at the data itself. That seems to be the issue. So let's look at it differently here. There, okay, 2008 works. So if no data, then we can't produce a result. So you can see we have a lot of names there from 2008 with a high frequency. And yeah, only two that are Jack and Sean that are most common those years. So here's 2008. Yeah, we had Jack was more popular than Sean, but Jack historically was actually quite rare. So there you go. You can look up your own name. So what we want to do is gather this name. So you can see there, it's a large data set. You got 46 columns. They're not in sequential order. But the structure is essentially the same. We just type in gather, type in our data set names, type in our key. We're just going to call it Y for year. Value is the observation. So it's the number of names. And then what we want at the end is the column names. So let's put a placeholder there. Obviously, the column names on its own is not going to give us an answer, but that's kind of what we want there. So a more easy way is given in the question here. If we take the data set names and check the structure, yeah, maybe the structure. When you look at that, you can see that it has there's 2004. 46 variables, the first one of which are just the names. So if we look at the column names, in names, that gives all the column names across the different years. If we look at the column names, one, that's just the name. So if we see what's in names, in that column only, it's just all the names. So you can see there are a lot of names. So what we want to do then is select the other columns. So you can see there we selected the other columns. Where are we? Yeah, you got 2 to 46. That'll be the other names. So we just want column names of names, excluding the first column. So that's actually what we're looking for. A slightly different expression. Yeah, that can work. Is there. So we're able to select all of these. If we wanted, we could actually drop like 2004 if we didn't want it. How would we do that? We could go from to 36, 35, 34. So I think that's column 34. So you just put in here 2 to 33 and then 34 to 46, I think. 35, 46. So you can see there, didn't work. I miscounted because there's one column missing. So there you have right 36, 35, 34. Yeah, so 34 is missing there. So now we can use this in our function we had before. And that's the columns we're going to produce only. So you could put them in there like that. In reality, we don't want to drop 2004 first because this won't give us a nice result. So instead, we just leave it in there and then we'll try to view this altogether because it's a lot of information. In fact, what we'll do is we'll assign it a new variable called names2 with a, there we go. And we look at the structure of names2. What you see there is it has 100,000 rows and just 3 variables, 3 columns only. So the name, the year, and the number. So let's view names2. There we go. You have the names. So AJ is the name, Ziad is the name, and the years. And then the numbers. So the most frequent number in a year was John in 1964, thanks to the Pope, I assume. And that was consistently high. And the other one is Patrick and Michael. As I said, these are Irish names. So there you go. So that means we were able to gather them and put them in names too. We can do the same for the Irish girls' names. And again, these are just to reflect biological data. Irish girls' names have more diversity, would you believe? And we find that there's 3,000 names and 40 entries, so they don't actually match. But we can basically do the same thing as we did to the boys' names, just with a different name. So we can go to gather names G, key equals Y for year, value equals number. And then we have the columns names for names G, and we're going from 2 to 39 because 2 to 40, because that's what it said here. But let's see if this works properly. Names G2 at the start. Let's check the dimension, the structure of names G2. So I'm not sure if it worked. So you got 121,000 entries of 3 variables. So let's have a look at it visually now. So we've gathered a really large data sets. So there we go, 1964, first of all. Many, many names. Yours might be in there, you can search. And then let's say, what's the most frequent name? As you would guess, it's Mary, all the way through the 60s, and then Catherine and Margaret start to appear as well. So that's gathering those 2 large data sets. And that allows us to do further comparisons that are more advanced. One of which is called inner join. So that gets us the unique shared names as a table to view them. So this function here is quite complex, but we're comparing our data sets. So starting with inner join, I'm just taking names 2 and names G2. If we do an inner join like this, a bit like dealing with genes, they have expression values. You have your gene or expression value. They're linked. But what you want to do is compare your genes. Say you have 2 different experiments. You want to say what genes or probes or features are of interest here. You might just want to take the name only. That allows more easy manipulation here. If we do this, what we'll find is that we get a lot of names. Okay. So the dimensions, because it is only 1 dimension, yeah, we got a lot of names. So these are the totally unique names that are present that are shared between the data sets. But if you noticed, when you looked at the names to the boys in particular, there's a lot of NA values here. So we go down. Yeah, even this scrolls down. So you go down further down. Oh, too far. Yeah, you see an enormous number of NA values here, which are not useful in terms of counting because they're entered in as a year, but they have a 0 value. So we actually don't need these. So to think more carefully about what we're trying to do here. So names 2. Let's get the unique shared names because there's redundancy here because we have each year had a different entry. So that's why you have unique there. So now we're down to 168 names, and let's sort them just for ease of understanding and viewing. That's the next part. So you can see there we start with, what's the first one? Adiola, then Elaine, Alexis, and so on. And we can look at them as a data frame. That's the final part as, let's say, view data.frame. It's just purely for visualizing it to understand what we did. So you can see we have our names there like that. But we know in the boys, there's lots of NA entries, so the accuracy is something we have to think about carefully. But the purpose of the vintage function, it basically compares 2 data sets and says what entries are present in both. So you might ask as well for the inner join, what years are also shared by these 2. So let's look at why. You can see there's all the years shared. We only want the unique ones. So there, you see there's missing ones in the girls, and that means that if we want to compare them, girls and boys, on an annual basis, we actually have to think about it more carefully. So what we want to do with the boys data set is take names, and we're going to subset. I prefer subset myself. And we're going to look at number. That's what we called it, greater than 0, greater than 0. So we're going to call it names. Let's call it boys so I can understand my code. Names, number. It must be value. Sorry. There we go. So we're going to look at names 2. And this is the one where we had number greater than 0 as a criteria. So if you look at the structure of boys now, you can see that's considerably reduced. It was 100 on 1,000 or so. Now we lost 80,000 of them. So 80,000 actually didn't really have information for us, just like biological data sets. We also want to eliminate NA values. So we do that as well. We're going to do and is.na is a function that will detect if something is an NA. It will return true if it is. So that's why we put an exclamation mark at the start, because we want false. Is an NA for number. So that will say if number is NA will turn true, this little function. So therefore we're saying we want this to value it as false. So we have false at the start. So this is number is 33, is NA will be false. So we switch it back to true, if that makes sense. So do that to boys again. The structure of boys is now, yeah, it worked. Okay. And we do the same to girls. So girls is a subset of names G2, where we have number greater than 0, and just for pedantic security is.na number. Okay, that should work. Structure of girls was 122,000. Now it's 28,000. So you can see it's considerably reduced. So let's go back to our inner join function. Yeah, just replace these with girls and boys. And there we can see we have a bunch of names that were counted and are present in both groups. So if you look at different differential expression where you have some sort of interesting feature you want to look at, that's a way of extracting that information between different groups where you have heterogeneity inside the data. Okay. Full join joins shows rows in either X or Y. So if we run this, we'll find that full join names is very, very long. So you can see there we have 50,000. So basically combines the data sets in essence. So if we view that, what you see there is that the boys are listed first. If you scroll down through, yeah, they're probably the girls' names. Then another one is right join and left join. So these differentially join the boys with all the rows in girls. So if we try that, we'll see we get 28,000. If we look at the rows that were originally in girls, so you can see that that's what we had. If we do it vice versa for left join on the boys, we see that that corresponds to what we had with the boys. And then there's other variations on like that. Like we have semi-join where we keep rows and boys with the matching girls, but it doesn't add the girls' info. So let's try that. If we try that and look at semi-join names, what we see there is that we have 35 observations with just 3 variables. So if you look at those ones, yeah, we can see of Vivian, Jan, Florence, Leslie, and so on, all present there. Then it's anti-join. So anti-join includes all the rows in girls, or in boys in this case, it should say. And then we can check. I don't think this has made any difference in this case compared to boys. Yeah. So to remove the ones that are present in girls, and retained only the ones that are unique to boys. If we switch it around, we just give girls as the first argument, boys as the second argument. Take the structure of, you see there, we have all the girls' names there, except the ones that are shared with boys. So that includes our introduction to tidy data with, or please look at demonstration video 2 for more on functions and subroutines.